Hello everyone, it's me, Joseph. Here's a recording of the EECS 470 Lab 7 slides that we're going to show on Thursday and Friday lab. This is going to be a two-part video. The first part is going to be just the lab slides, and then the next part will be we'll show some Verilog examples of what we're talking about. So here's just an overview of what we're going to talk about. So just some quick stuff about the project, and then we're going to get into memory, some more relevant system Verilog features, the iCache controller, how using memory bus works. That's going to be in the Verilog part mostly, and then some things about prefetching, which you'll find very useful for getting better performance in your final project. So, just a reminder, our milestone 2, that's due on Thursday, March 26th. So that is 13 days, just under 2 weeks from this recording. The primary goal you should have is to be able to run our molten LSQ assembly program and get the correct output compared to the in-order pipeline, right? So remember, molten LSQ is just a test that uses simple multiplies and branches, right? But no actual loads and stores. So it doesn't require your LSQs working, but it expects that pretty much everything else. So that's going to be the function units, all the scheduling, and like at least some basic branch prediction is functioning properly. So even once you get the execution parts running properly, you'll find that it takes quite a while to actually connect all those things and then verify that those are working as well. So definitely get to that as soon as possible. So here are some project-specific rules for the cache, mostly and for our CDBs. So here, this is actually wrong. For your cache size, we're saying you have 256 bytes for both the data cache and the instruction cache, right? So that's going to be 32 by 8. I mean, technically, this split can be whatever you want it to be. But I would recommend 32 by 8. That makes the most sense with the memory controller, as memory controller only allows for up to 8 bytes to be transferred in either direction. And you'll also have the ability to have a victim cache, right, of up to two 8-byte blocks. So that's just two blocks. That does not include the metadata, right? We're just saying that the data in the victim cache cannot be more than 16 bytes. Right. Also, for your CDBs, remember your CDB can be no longer than your actual superscalar width. So if you're two-way superscalar, you can have a four-way issue, but your CDB must be only two-way. All right. So the primary focus of these slides is going to be on, again, using the memory system and then how to basically how to use caches with that system. Again, a lot of this stuff is going to be examples. They're not, I would say, particularly good, but they are simple enough, I think, that we can cover them in this video, and it should inspire you on how to make. And you'll see, I think, some very simple and maybe not so simple ways that you can make them better to get better performance. All right. Remember the goal again, not to try to use everything, but always remember we want to make the common case fast. Right. So you want to optimize all the things that we think are going to happen the most often. All right, and then also based on like what type of things you're doing in your project. So if you want to have prefetching, then you probably want to have a non-blocking cache. Those just kind of go hand in hand. All right, so the memory unit, as you'll see, is in the actual test bench folder of your project. That's because memory is not synthesizable, right? So you have your processor core, and that's going to be made of all of your scheduling and out of order units, and then you have your cache, which is also going to be in your processor core. All of that's going to be synthesizable, and then you're going to plug that into your memory unit, and that's really just going to be some Verilog code that's pretending to act like a real module, doing things like synchronizing to its own clock or to the same clock, really. But that is not actually synthesizable. It's in this file mem.v. If you're ever confused how it works, you can read the file. It's, I wouldn't say straightforward, and you shouldn't have to read the file to understand how it works. We're going to cover that today or in these videos. But yeah, just keep that in mind. remember that the memory, it's clocked at the negative edge of clock. So when the clock, it changes its outputs every negative edge. So while you can read them at the positive edge, right, just fine, sometimes you can't expect that the value you like in your combinational logic to always reach the positive edge and satisfy your setup and hold times, um, because of this changing at the negative edge. So you may find it simpler to maybe add a synchronous buffer where your inputs to the memory are clocked at the positive edge, and then the outputs for those previous inputs are clocked at the negative edge, just so that, again, maybe the timing will make a little bit more sense when you're looking at it in the waveform viewer. Also, for the RISC-V instruction set, the address space is 32 bits, but the memory is only 64 kilobytes in size. So you'll probably see that you can use this fact to simplify some of your designs, mainly just save space and then save a little bit of clock period, because you don't have as big of an address space as this may imply. All right. So, and then these are, for example, the responses as you see here, right? The mem to proc, right? So this, when you see this mem to proc prefix, that means that this is a wire that's going from the memory to the processor, and then this is going to be what the content of that message is. And so this is going to always change the negative edge of clock. Okay, so moving on, you probably saw that here we have this thing called a tag. So this tag, right, the memory is just, it's essentially RAM. You can think of it as RAM, where you just index it by an address. So that tag is not going to be a cache tag, for example. It's more of like a ticket. So in this example, let's think of when we say, when you go to a restaurant and you make an order, they'll give you a receipt that has a number on it. Your order is ready. When they call that number, you'll head to the counter and you get your food. That's kind of the idea here. Every time you want to do a memory request, you send the request, the memory will say, here's your ticket, that's the response, and then you're going to look at all the tags that are coming out of memory. So you need to save your response. Once the tag that you're looking for is called out by memory, then you can go ahead and say, that's my data, I'm going to read it, and then I know that I don't need to look for any more tags. One thing to realize, just a side note, is that these tags only are important for load instructions. For store instructions, the memory does not really say that the store instruction completed. You can just assume that once you've sent a store instruction, that any load sent after the store is going to get that. If it's to the same address, they're going to get the right data. All right. So also, I guess, just some idea behind the motivation behind tags is that, right, if we just used addresses, one, that's more wires than we need, right? The tags are just going to be 4 bits, right? But if we use addresses, then we would have to use technically 32 bits to track those. And that's also not clear to say, well, did the load complete, or did the store complete, or if we have multiple loads, but let's say some of them are canceled due to a branch prediction, right? We don't want to have any of that ambiguity. So a tag is sort of an absolute thing. You can send loads to memory that essentially don't actually, that maybe get canceled, and then the tag kind of just like goes in the garbage and you don't do anything with it. That's a valid behavior. So here is the interface for the memory module. Remember, even though it looks like a Verilog module, it is not synthesizable. There's just some clever loops. So we've got these signals, proc to memory. So that's going to be things going from the processor to memory, and our mem to proc, those are going to be going from the memory to the processor. Right, so we've got our address, data, and command, right? So this command is an enum type. I think here it's just used as a 2-bit wire. If you want to use the actual enum, right, it should be called bus under command. Right, so you can use that, and it has 3 values: bus none, bus load, bus store, and these would be, I believe, be 0, 1, and 2 appropriately. So this is sort of like the internal signals. These are what's kind of used for the scheduling. So the memory itself is a FIFO queue, right, where you send a request and then it comes back a constant number of cycles later. So the memory has a 100 nanosecond latency, but depending on your actual processor's clock speed, that will be that you're going to want to fix that to an integer number of cycles that it takes for memory to complete. So you'll take 100 nanoseconds, divide it by your clock speed, and then round up to the nearest integer. That will say how many clock cycles do I need to wait before my request is done. So these are two parameters that you'll find in sysdefs, which says the memory latency in cycles, and then the num tags. So memory latency in cycles is just what we talked about. We're going to divide that by your clock period, whatever you can synthesize it to. The default right now I think is just 10. That just assumes 10 nanosecond clock period. And the num tags says how many outstanding requests you can have at the same time. So if your clock period is less than 10, then it is possible for you to sort of overflow the memory, and in that case, right, then you'll get what we call like invalid requests. We'll talk about those later, where the memory response says that we can't accept your request because you've maxed this out. You've maxed out this value. All right. So in the memory, when you send a proc to memory command, you're going to get a response. So that response just says, what tag am I going to wait for? So every time you send a command to memory, you need to wait for the tag, because memory does not give you any data back instantaneously. The only time you wouldn't have to wait for the command is if it's a store, right? If you send a store to the memory, you can assume that it sort of just happens eventually, right? And then also that if I load from that address again in the future, that all my loads are going to happen properly. I don't have to verify that the store worked, right? That's we're verifying the correctness of stores using all the out of order mechanisms that make sure we commit all of our stores in order. And then also we have a tag, so that's going to be the things that are completing in memory. So again, you can imagine the memory as this FIFO queue. So we're going to send requests here, and then we're going to get, and here the memory is going to check and say, here's your response. And then here we're going to get data back out here for our loads, and then the memory is going to say, here's a tag. And your processor is going to plug into this, right? Probably really just your LSQ and your cache controller. It's going to plug into this, and it's going to look to see, am I sending my response? Did my response work? And then did my tag work? Did I get the tag for data I'm waiting for, right? And are any of my loads that are waiting for data, are they finishing? All right. So when you get a response, right? So the response is going to be a number between 0 and 15, right? That's 16 numbers, but we're saying there's only 15 valid requests that can be in flight at the same time, because 0 is going to be our special case, where if you receive 0 as your response, that means that you need to try again, because one of these three things happen, right? Either you didn't have a command, so you don't really try again, but you're just not doing anything, or the address was too big or invalid in some way, like unaligned, or the maximum number of requests, like as we said before, you filled up the memory buffer. So the tag means that it kind of means the same thing, right? So when you get a tag back that says that matches one of your tags that you're waiting for, you can then take the data. That data is only the data and the tag. They arrive at the same time, right? So you'll see data and tag. They're gonna always arrive like at, or they'll really change at the negative edge of clock, but they're gonna always, when you check them, if the tag matches, then the data is for that tag. You need to get the data at that same clock cycle. Otherwise, when the tag is 0, that pretty much implies that the data on the bus is invalid. You should not try and read it. I believe it will be set to X in the simulator. All right. So we're assuming the memory latency is non-zero. The only way you could get 0 cycle latency is if your clock period was 100 nanoseconds or something like that, which again is essentially useless. All right. So it's just a pipeline. All the loads can go in in any order, and then as long as the store gets into the memory before the load does, then the load will get the right data, assuming that they have the same address. Another thing that's important to know is that your memory controller, right, you have a separate cache for instructions and a separate cache for data, right? And you might also have some other things to talk to memory, namely this prefetcher. And so you're going to need some sort of arbitration that's going to say, I have my memory here, right? This thing has a FIFO request buffer. And so in your CPU or in your core, right, you're going to need to say, here's, for example, my iCache, here's my Dcache, here's my prefetcher. All of these are going to need to go into some sort of like mux or arbiter that determines whose request actually goes through, and then also responds, right? Let's say ideally, right, if you have your D cache is asking for data, or your data, your LSQ or data cache controller is asking for data, you want to prioritize those, right? You probably rank this as 1, 2, and 3, right? You want to prioritize your data cache requests over your iCache, right? And so your data cache, when it sends request memory, it'll get back a tag, but then your iCache should say, oh, your thing failed, right? So this is sort of like this arbiter is going to virtualize the memory responses, right? So the data cache can get a can get a tag, a valid tag, but the iCache might not get a valid tag, right? And that's what the arbiter is going to do. It's going to say, iCache, you sent a request, but because the data cache also sends a request, your request is denied, not because of memory being full, but just because there's someone with more priority asking for data. All right. So this is logic about how memory controller sort of just or determines which request is ready to finish. Again, you don't really need to understand how this works. Again, it pretty much just counts down from the latency to 0. When whichever one reaches 0 is going to broadcast its tag and say, all right, I'm done. Whoever's waiting for me, here's your data. Take it or leave it. And then wait for, and then eventually that tag will get reused. So again, this is more of the same. Again, not too important. It probably will make more sense to read in the actual Verilog file. One thing I will add though is that if you see here when it says loaded data, it reads 60. This is reading 64 bits or 8 bytes. For a memory controller, you're allowed to use the interface that sets the write and read size. So you can do read and writes of double or word. So it's going to be 4 bytes or 8 bytes, right? So double is 8 bytes, and then word is 4 bytes. You can use that interface. I think it's called mem size, something like that. We'll see it in the Verilog later on. So you can use those. Obviously, the double or for the RISC-V instruction set, you'll see that all of the loads and store instructions are going to really just need this word-based mode because they can only read up to, your registers are only 4 bytes in size, so the loads and stores only do up to 4 bytes. But for your cache, right, so this is going to be load and store. But for your cache, right, you're going to probably want an 8-byte block just because if you're super scalar and you want to read 2 instructions, right, you're going to need 2 instructions in your cache somehow. So this is where you're going to need, for your instruction cache and your data cache, this is where using the double mode is going to come in handy. Now, this really only happens in your iCache controller, right, or in your Dcache controller, where they're going to directly communicate with the memory to say, write back this like 8-byte cache line, or load an 8-byte cache line, or if you have a write-through cache, then you can do a 4-byte store or a 4-byte load. Right. All right. So again, yeah, this stuff's not too important. So remember, your memory, like, it kind of comes in 2 parts, right? You have this mem.v, right? This is just a test bench, right? And then you have your pipeline or your core. There's going to be your synthesize design, right? And then they're going to connect somehow, right? And then this is going to be in the overall bigger test bench. So all of this right here is going to be Verilog that you write. You cannot change this, right? Do not change the memory, any of this. But whatever you do with the data that you get from the memory, right? For example, you have a cache in here, right? And you have an LSQ in here, and you've got a bunch of other stuff inside the core. You can do whatever you want with that stuff, with whatever data you get from memory, but you cannot change any of the stuff in the actual memory module. All right. So one thing you'll probably find useful when you're designing your cache is some more system Verilog data types that we talked about before, which is the union. So you've seen this example, right? We have this struct called a cache block, And so what we do is it's actually a union where we have these types, or these sort of like addressing modes. And so we have a double, word, halves, and bytes, right? So double says we're going to treat this thing as 1 by 8 bytes, or we can go into words where we're going to keep it by 2 by 4 bytes, or it's going to be into half words, which would be make it 4 by 2 bytes, or we can treat it as all as bytes, where it's going to be 8 by 1 bytes. Right. So all of these overlap the same data, right? So we have our double would be, this would be 8 bytes, right? Or we could change it, cut it in half into 2 sections. Excuse me. Or we can cut it into 4 sections, or we can cut it into 8 sections. Whichever way, the data is all the same between all of these, but we can decide how we want to index this using these parameters. So here's an example in just like always com block, where we're going to take 64 bytes at once and assign it to the double, or we could assign 64 bits, my bad, 32 bits, which is 4 bytes, to one of the words, right? This is the top word. Or we can change it to the third byte. We're going to write 8 bits, or 1 byte. So now, common example where you'd actually use a union is, or not outside of this cache block example, would be if we're looking at an address. Let's say we want to have an address type. We can have our addresses, if we have like a direct map cached, would be, if we take we start our address as just like a 32-bit vector, and it's going to be split up into a tag and a set index and our block offset. So we can change what partitioning we have based on what context we're looking at this address at. So if we have a direct map cache, then we're going to have our tag is going to be, in this case, 18 bits. Then we have a 11-bit block or set index. Because it's direct map, that's the set index and the block number, I guess, could be used as the same thing. And then we have our block offset. We're going to say it's 3 bits because we're just going to say it's 3 bits. We could also do the same, or 3 bits for 8 bytes. We could also do the same for a set associative, where we have slightly more or slightly less sets, and then therefore the partitioning of the set index in this case will change. But again, when we create an address struct right here, the union is going to contain both of these at the same time, and we can decide in what context do we want to address. Do you want to address as a direct mapped or as a set associative? It's up to us. So moving to, or on the topic of caches, we'll talk about the iCache controller. So in the project example, we have an iCache controller that you can use just as, like, as I said, it's not, as we said before, the examples are not necessarily very good, but they work. And if you just want to see an example of something that will work if you're not sure how to do it, you can use these for reference. So here we have an iCache controller. You'll see this in the iCache.v. The iCache.v file, where it's we call this a blocking cache. So what that means, if it's blocking, that means that if we get a miss, then we're going to essentially hold the address line constant until that miss gets resolved. So we have this current tag, current index, and we just index, or we just split it up, right? These I think the current index is probably like a 5-bit wire, and the current tag is probably a maybe 10-bit wire, right? So this assignment is going to take the first 5 bits of this vector range, and then another 10 bits, and it's going to assign them into these wires appropriately, right? That's just what it's trying to do. It's kind of clever, I guess. And so every cycle, the iCache is going to store the last index as to the current index. So imagine in our processor we have a fetch stage or fetch module some way that's going to plug into the iCache, and then this is going to plug into some sort of cache array, but then it's also going to plug into our memory test bench, right? And it's going to bring data from the memory into the cache if it needs to, and then also read from the cache and send data back to the fetch if necessary. So we have this wire in the Verilog code, for example, change wire. Whenever the current index and the current tag differ, then that means that we've changed our address. So we want to track this because we don't want to just keep if we get a miss, we don't want to just keep sending memory requests, right? Because that's just going to fill up the bus. So only when we detect that the address changes and we get a miss, you'll see where the and we get a miss part comes in later. When the address changes, we'll then decide whether or not we're going to send a new request. Otherwise, we're wasting memory bandwidth. Um, which again, since the iCache is probably the lowest priority, or if the iCache is your lowest priority, then that's not like a bad thing. But again, just for best practices, you don't want to send memory requests and keep discarding them for no reason. So when the iCache gets a hit, what it checks is it says that so the iCache is going to look in the cache mem, right? It's going to send some index and tag bits to the cache mem. The cache mem is going to do it. It's pretty much a CAM, right? Content addressable memory. It's going to check to see does that tag and index match. If it does, it's going to return a valid bit. That's your hit. You're pretty much going to forward your valid bit to the fetch unit, and you're also going to forward the data. All right, and the fetch unit will only use the data if it says it's valid, implying that it's a hit. So I guess the important thing to realize here is that in Project 3, we saw that the fetch unit was essentially reading memory, but here it's really reading the cache memory. So before the fetch reads, so anything the fetch reads is actually in the iCache, not in memory, right? It will send a request to the iCache. If it misses, the iCache will bring that data into memory or into the cache and then read it back to the fetch. Right? You can optimize that and try and do it in the same cycle. Again, that's an optimization that's up to you. So the way the iCache decides whether or not it needs to send something to memory is if you have this unanswered miss wire. So unanswered miss is going to check to see did we change the address. Then if the address has changed and we got a miss in the iCache, then that means that we need to send something to the memory controller. However, it is possible, like I said, if you have data traffic going to the memory controller, that first time we changed the address, you didn't get a response because the data exceeded you in priority. It beat you, I guess, in priority to the memory controller. And so you're going to keep trying as long as this miss is outstanding, right? Miss outstanding kind of checks to see did we fail last cycle to send a request? If so, then we're going to try again so long as this response is not 0, right? So if the response is 0, this implies mem denied the request. And realize we care about the response for the iCache because iCache is always doing reads. If it was, for example, for some reason doing stores, we would not care about the response. Or actually, no, we would still care about the response to make sure that it got into the queue. My bad. So I take that back. So yeah, so whenever you send a request to memory, always check to make sure that the response is not 0, right? If it is 0, then that means that the request you sent did not go to memory, and so you need to try again the next as soon as possible. All right. So whenever you have an unanswered miss, then you're going to send this bus load command, and with whatever address that you have. Sometimes, right? Let's say that you're holding, let's say you're trying to fetch an address, but then the processor decided that, oh, there's a branch taken, so the address you're fetching doesn't matter anymore. We're going to a new address. Then, right, that change address would help because now you're going to send a new command to the fetch unit, says change your address changes, and then we're going to clear the miss outstanding, right? We're not going to care about what we were trying to fetch beforehand. That's kind of what this update that's part of the conditions in this update mem tag. This is going to say what mem address or what mem data we're waiting for, because we might be able to send a request to the memory controller for an address, but if some sort of exception occurs, we're not going to care about that address. Again, most common one would be a branch misprediction. With the branch misprediction, we're going to reset the mem tag to 0. In that case, because now we're going to need to try and send a new request, or maybe we get a hit in the cache for the new branch target, right? So we essentially wanted to discard the old mem tag. So when the memory when the memory completes a command, it'll say mem tag is this. But if no one cares about the mem tag, the memory is not going to wait for someone to confirm that they got the data. It's going to put out the mem tag. If you need that data, you have to read it in that clock cycle. Otherwise, the memory, you have to try again. The memory will move on to whatever is completing on the next cycle. All right. So I think this is more of the same, right? Where you get a branch condition and then you change, yeah, the address will change. And so this data write enable, this is writing in the cache, in that cache mem. So also for your iCache controller, right? As I drew that diagram before, you have your iCache and then you have the actual cache memory. So the iCache is going to be writing to the cache memory, and it's also reading it to check to see if it gets a hit. So that's what you do this data write enable for. So there's another module. It's pretty much just a big bit array that's going to be, we call it cache mem. Excuse me. That's all of the data that's used for your cache. That's for storing of the cache, like tags, valid bits, and it'll be set associative however you want. You can parameterize that. I would say it's a good idea to parameterize that however you want to do it. All right. So I think here's just an overview of the iCache controller. So again, there are some optimizations. Say for example, if you get a miss in the cache, what the current implementation does is it first tries to read the cache in one cycle, then the next cycle determines that the cache read missed, and then so what will happen is it will then now send a request to the memory. You could do all that in one cycle. Again, there will be some penalty on your clock period, although it's unlikely that this is probably not on your critical hit. So we could send, right? So this is an optimization. We can send a request to the memory in one cycle, but we have to make sure that the memory can be read in less than one half of a cycle, right? Because the memory unit or the cache memory has to be read in one half a cycle, because the memory unit updates its outputs about like confirming or denying whether or not a read happened or not. It updates those on the positive edge of clock. So if you cannot read your cache mem in half a cycle, then you will not be able to you will not essentially get this one cycle benefit, right? You will essentially still fail, because once the negative edge of the clock happens, right, you have to wait until the next negative edge of clock before the memory will acknowledge your new request and say, can I do it or can I not do it? All right. Another useful thing is prefetching. You'll find that prefetching with your instruction cache is almost necessary for good performance. As you start a test case, for example, your iCache is going to be empty, and so you're very likely that you're going to need to at least like the next 5 or 6 instructions. You're going to execute them. So you want to, when you miss on an instruction, it's nice to have a prefetcher who's going to say, I missed this instruction. Let me get the next, powers of 2 are a good number. Get the next 2, 4, or 8 instructions. Bring those into the cache so that I hopefully will execute those and get better instruction level parallelism. All right. So now moving on to dcache controller. Dcache controller will be more of the same. The only thing is that now it has to handle writes. So you have writes to the cache and then also writes to memory. For the most part, it's again, I think it's most of the same stuff. Just remember that when you write to memory, you don't have to worry about getting responses. You just write, and then when you're depending on if you have a write through or write back cache, that can change how you'll see the conditions. We'll walk through a example of how I guess to make dcache faster. Actually, it's right here. So as I said before, the other cache, the iCache that we've provided you, is a blocking cache. That means that when you get a miss, you have to wait for that miss to resolve. So with an iCache, right, sometimes you get lucky where you get a miss, but then it's actually a branch, and then maybe you branch to a PC that you don't miss on, and then maybe you get lucky. But with the dcache, right, if you get a miss on a load instruction, you need to resolve that miss, right? You need to get that load's data, and then if we're blocking all of our loads, right, so the first load instruction misses, and then the next one misses, now as you saw before, we had a parameter that says mem latency in cycles. So if it takes 10 cycles for the memory to get one address, then 10 cycles to get the next one, right? We're now serializing all of these misses. That's going to hurt our performance a lot. So it's good to have a non-blocking cache where you can overlap, right? We want to overlap misses. And so the way it's done is what's called miss status holding or handling registers. So this keeps track of all the misses that you've incurred over like or in a certain period of time, and then you can send all these requests to memory and also still incur more misses and overlap the execution of getting them from memory. Right? Remember, the memory is pipelined, so you want to take advantage of that. And using MSHRs, that's how we do that. So each MSHR is just going to be tracking the tag, address, and then data values in case it's a store miss. And yeah, it's going to be very similar to like a reservation station and a ROB, as we'll see. And of course, it will increase your complexity, right? It can be a little bit hard to think about, but it will also increase your performance by, I think, a worthwhile amount. So again, the big idea is we want to, every time we get a miss, we're going to allocate a new MSHR, right? We have a constant number of those. So the MSHR only works to a certain point. Once you run out of MSHRs, we can't get any more misses, right? That's essentially the main idea. So here's an example of what this would look like. So we've got this program over here, right? This is like what our LSQ is going to look like. And also, if you want to, I guess, skip ahead to the end of the lab slides, this part will take, I think, quite a while. But here's our program, right, in our LSQ. So we're going to only do loads. So these are the parameters we have. We've got num mim tags 3. So we're saying we can only accept up to 3 requests at the same time. We're going to only do loads, and we're going to say the memory latency is 5 cycles. One thing that you'll find useful for debugging your project, or not debugging, but for finding bugs in your project, is this value. So even though we say you set this to 100 divided by your clock period, you might find that, or you will probably find that you can find more bugs if you change this value to a different number, just like, I guess, for fun. Because, well, especially like for lower numbers, you can get more intricate interleavings of the instruction execution, because maybe instead of a load finishing in 5 cycles, it can finish in 4, and then that causes some other branch or whatnot to just move in a certain order that just finds a deadlock or a wrong execution. Excuse me. Perhaps some ships passing in the night case that exposes a bug in your processor. So sweeping this from like maybe from 0 to 10, I think would be a worthwhile, or more than 10 would be a worthwhile endeavor. All right. So we're going to say that our processor is going to be 2-way superscalar. And so we're going to move through all of these loads in LSQ, right? So we're going to, since 2-way superscalar, that means that we can allocate 2 MSHRs at the same time. So this right here, this is our table of MSHRs, right? It's got all of these parameters. This is our LSQ. And then this is the memory like pipeline of requests. And we're going to assume like our cache is fully associative if we wanted to say that maybe these hit in the cache. So we'll get to that. So our first thing, right, we're going to say at time 0, we're going to run these first 2 loads from the LSQ. So at time 0, we're going to get, say, address A, address B, right? They're going to be a both type load. And then the mem tag is going to be 0 because they haven't been sent to memory yet. And they're also not going to be done. And the data is going to be X, right? We don't know. So another important thing that you're going to need for your MSHR, if you're going to implement this as sort of like a circular queue, you could do this as a reservation station type where you just have like a priority selector. I find that the circular queue method might be easier because it requires less priority selectors, which is, that's kind of some expensive camming. So what we can do is we can have some pointers where, let's say, actually, I'll undo this. So before we start, we'll say we have a head pointer, we have a send pointer, and a tail pointer. So your ROB probably only has a head pointer and a tail pointer. But in this case, we're going to have a send pointer, and that send pointer is going to track, as I think I might have skipped over this here. I think it's somewhere else in the slides. But the idea is that we can allocate MSHRs, but we can only send one request to the memory at a time. And so what we have to do is we have to track which ones have been sent and which ones have not been sent. So we're going to start our head, send, and tail pointer all at the same position. And then we're going to allocate right? We're gonna allocate two MSHRs for these two. Let's assume that both of these addresses, A and B, let's assume that they both miss. So now our tail pointer is going to move to 3 or 2, right? However you want to index that. And it's going to add time 2. They're going to be allocated with address A, address B. They're both loads. All right, they both have no mem tag because they haven't been sent yet. And then their done is going to be 0. And the data is X because we don't care. All right. So that's time 0. So now at time 1, we're going to have the send pointer send a value. So let's assume that we'll assume that these ones below these can't be executed yet, right? They're not ready. They don't have their address, for example. So at time 1, we're going to send at time 1 we're going to send this first request, the one that's the send pointer, because it hasn't been sent yet. So it's going to get a mem tag of 1, right? So this one was received at time 1, and we're going to say it's going to finish at time 6, right? Our memory latency is 5 cycles. And so and we're also going to have tags inside the LSQ. These tags are going to be these tags are not going to be related. They're not related to the memory. They're actually related to the MSHR. So these tags are going to be the N for whichever MSHR they belong to. So here he's going to belong to MSHR 1, and then the second node is going to belong to MSHR 2. Their status will probably be waiting. All of these should have been set at time 0. It's my bad. And the data, right? They don't have their data yet. All right. So you've gotten those. Now let's say we want to dispatch, or not dispatch. Let's say we also want to send. Let's say we want to send this guy. Let's say at time 2, we're going to send n equals 2. But also at time 2, let's do it in this order. Before we send these, we're going to add 2 more misses, right? We're going to add these next 2 guys. Or actually, let's just do a special case. So we'll try and add these 2 guys. But one thing you might notice is that let's assume this is a unified LSQ. So if this LSQ is unified, that means that there is no difference between these 2 loads, right? With respect to the results, the results are going to get the same value. So you notice that we have an MSHR. We already detected MSHR for this first load. So we can do what's called load coalescing, where we're going to determine that this guy is going to also they're going to combine into the same MSHR field. So let me erase some of this extra stuff. So instead of him getting a new unit, right, they could share units, right? This is an optimization. You don't have to do it like this, right? But an optimization would be if they share units, then I don't have to use all 5 of my MSHRs to hold them. I could use only 4. Sometimes this may or may not be a good idea. For example, let's say there is a store that actually was a store in between here. In this case, because they have the same address, they cannot coalesce, right? So that's just a thing you have to watch out for. But let's try and see, I guess, what that would look like, right? So this guy's going to get the same tag to wait for. Remember, that tag refers to this N. And we're going to dispatch 2, so we're also going to dispatch C. So C, we're at time 2. So C is going to get a new MSHR. He has no tag. He's not done. No data, right? Tail pointer is going to move forward by 1. Okay. So also at time 2, we're going to send request B, and we're going to expect this to finish at time 7, right? These haven't finished yet. We don't know what their data is, but we'll dispatch this time 2, and then since we've sent this one, we can also on the next cycle we're going to advance the send pointer. This guy's tag is going to become 2, and then the C is waiting on 3, right, So now we're at time 2. So now we can move forward to time 3. Let's say we can dispatch, or we can allocate for D. Oops. Yeah, so this is at time, yeah, so time 3. And this will finish at time 9, or no, time 8. Oh, oops, my bad. So so the MSHR gets allocated, and then we're not going to send it until um, we're not going to send it until the send pointer reaches it. So allocate this one. So address is D. It's a load. No mem tag. Done is 0. No data. All right. Also at time 3, what we can do is we can send request. We can send MSHR number 3. So time received will be at time 3. It's going to be expected to finish at time 8. All right. And the send pointer, because we've sent it, right? Mem tag's gonna be 3. Send pointer goes up by 1. And also we need to update the LSQ. So his tag is 4. He's waiting, no data. All right. So now we're at time 4, and I believe nothing can happen because we've maxed out all of the memory tags. So we can't send this guy, right? Can't send. Right. Well, you'll see that you'll put bus command as bus load or whatever, and you'll see that the bus response would be 0 because you cannot send. So you cannot advance the send pointer, and you cannot change this mem tag. So up until time, we won't be able to send this guy until time 7, pretty much. So let's say the next event is going to happen at time 6. So at time 6, what will happen is this guy will finish, right? So now we're at time 6. So it'll broadcast a tag. This MSHR is looking for tag 6, or for tag 1. At time 6, it'll change its done to 0, and then data will come back, right? Let's say this is 1. And so this one is done. It's essentially ready to be completed, but we're going to do that next cycle. So now at time 7, we're going to get a lot of things happening. So at time 7, let's first do the memory. So this guy finished at time 6, so we can erase that one. At time 7, we're going to also finish number 2, right? So let's say he gets data 2. And then, give me 1 second. And then, so we're at time 7. So this one's finished. So we'll clear this one out as well. And then the head pointer, or my bad. So looking at the head pointer, we can see that this request is finished. The first request is finished. So what we're going to do is we're going to broadcast our tag back to the LSQ and say, essentially move the head pointer forward by 1. Say this guy's done, right? We're going to move the head pointer forward by 1. The load for A is going to finish. And so the status is going to be, we could say it's done. It's got a date of 1. Now remember, we coalesce these loads. And so the load for A, for this one, right, again, they're tied to the same tag. So this guy is also going to finish in the same cycle, right? So this is the performance benefit we get from coalescing. Both of these guys, they essentially overlapped their execution, and so they can finish at the same time, even though one of them came later than the other one. So the tricky thing again to realize is that if you had stores in between them, right, you could not coalesce them, right, because a store might have the store to the same address, right? That could have invalidated your data, or there also is a scenario where, let's say that you allocate this guy at the same time this this one finishes. So say you allocate and this one was finishing, the first one was finishing, then they would take the same tag, but this guy would not realize that, again, this is ships passing in the night scenario. The third one would not realize that the first one had finished the same cycle that he copied its tag, and so he'd wait for tag one, which may come later on and just be the completely wrong data, right? So you'll have to also check for, for same cycle completion to make sure that you're not missing the data that you actually were looking for because you came at a, I guess, inopportune time. And that's where, for example, changing that memory latency might help, like sweeping across those values, because you can get these interleavings that will help you find your bugs. So you finish this guy, right, and pretty much this entire row, right, is done, right? These guys are free to complete and go to the CDB, get retired, or get canceled, whatever happens to them. So again, we're at time 7, and so the other one had completed, and so since tag 1 in the memory had completed, what we can also do, right? That was cleared at time 6. We can also dispatch this guy as 1, right? When we put this guy on the memory command, the memory will give us responsive 1. So this is received at time 7, and this is going to finish at time 12. All right. So now we can move on to time 8. So what's going to happen here, right? This guy is going to finish, all right, number 3, and it's going to finish, all right, gets value of 3, whatever that could be. Also realize when you bring in the cache blocks, or whenever you bring in the memory reads, you'll probably say, for example, OXA is also in the memory, right? It has a value of 1. Excuse me. And so is, now that we just finished number 2, right? OXB, it's got a value of 2. So yeah, this one's going. So that was it. So that's finished. Okay. So MSHR is 2 is finished, and so now we can broadcast back to the LSQ and say that load B, your data, you're all good. It's got a value of 2. And then we can also, right, for cycle 9, right, this can all go away, right? This is all done. Head pointer moves forward by 1. Also, since this guy got sent, the send pointer moves forward by 1, right? So now next thing, right, this one can be sent back to the, so because again the done is satisfied for the head pointer, then we can say that you're done, send back to the memory, to the LSQ. So that's for C. So it's done, and it got a value of 3. So we can clear out this MSHR. Head pointers here, right? Also, since the broadcast happened for that one, that was at time 8. This tag is not occupied memory, and so we're at time, I think, 9 or 10, right? I think we're at time 9. So for time 9, 10, and 11, nothing happens. At time 12, this memory will finish. So goodbye memory, and then this is done. And then at time 13, right, after 1 cycle, we're going to check. Again, you could do a same cycle check. Again, that can hurt your clock period, and it can also cause other issues that you just make sure you have to account for. So at time 13, we decide that the head pointer is done. So you broadcast back to LSQ with the data. So yeah, this one's data would be 4, and then we update to LSQ at time 13 with the data. So this data got updated at time 12, and we updated the LSQ at time 13. Right, and then we would also update the cache. Forgot the C and D, right? So those would also get allocated in the cache, assuming that they didn't evict or anything, didn't evict these other lines. We're just saying it's fully associative, so it should be fine. So after that, all the MSHRs would be free. Although like the head pointer would not be at 0, right? It would be here. So that's an example of how you do your MSHRs. There are some optimizations that I mentioned. There are some that I didn't mention. Those are up to you to decide on doing. Your MSHR can be pretty much as big as you want, or actually that's not true. You shouldn't make it too big because that will hurt your clock period. And then also realize that you can't if you store too much data in this, like if your N is too big, this is sort of like a cache that's like you can't read. Ideally, whenever something completes, you want to send it to the cache so people can read it. Yeah. Okay. So again, what about stores? So this example only did loads. Realize that when we send stores, they just get sent, right? They can be sent, and then they can kind of ignore them. They don't really need to do anything else because all the loads following them to the same address, they'll get the right data as long as you're maintaining the correct ordering within your own processor. All right, but remember, when the response is 0, then you cannot. Then the send did not happen, right? It was denied by the process by the memory. So you need to make sure that when you send stores, that you are sending that they're actually getting sent to the memory and not rejected. Right. So the question is, do we need to track stores in the MSHRs? Well, I think again for this reason, yes, you do. Right. If you're depending on what your cache write policy is, right? If you have write through or write back, that will determine how your stores where your stores are sent to. So if you have a write through cache, when they commit at the head of the ROB, you can send them to the cache. You can send them straight to the cache and to the memory, and the cache can sort of ignore them, but you still have to make sure that they still got sent to the memory, right? If it missed in the cache, it's fine, but you still have to make sure it gets sent to the memory um, by checking the memory response to make sure that the store command or the bus store command went through was accepted. If you have write back, then your MSHRs then you'll have to check, did I get a store miss? If I see a store miss, then I have to do MSHR, essentially MSHR that's going to write to the memory instead. That's assuming no write allocate. If you have write allocate, then your store miss turns into like a load and a store where you're going to load it into memory and then overwrite the value as you put it in the cache. So again, it can be as complicated as you want. That is mostly up to you. Yeah. So another important thing to know about your cache architecture is prefetching. So the idea of prefetching is it says I'm going to get data, I'm going to read data into my cache before I need it, or more accurately, or sometimes read it from or send the request to memory before I need it. So prefetching is, I would say, pretty much necessary for your instruction cache, and it can be useful if done properly for your data cache. Although it's a little bit hard to predict, right? With your instructions, doing what's called next line prefetching, where you just get the next line or the next 5 lines of cache for each instruction miss, that can be useful because your instruction read pattern is pretty predictable. You're going to go from PC to PC plus 4, 8, 12, 16, and so on. But with a data cache, right, sometimes you're in an array, sometimes you're in a linked list, sometimes you're in a binary tree. You never actually know. So again, usually again with prefetches, for our processor, we're not running super complicated programs. So keeping the simplest method is usually the one you'll want to at least start with. And then if you think that you can identify other patterns, go ahead and try, analyze them, and see if they're worth anything. So I think this is mostly what I had said before. So remember when you prefetch, if you prefetch too much, that can like eat up your instruction bandwidth. That's why sometimes you can decide what do I want to have more priority, right? My prefetcher or my instruction cache. I'd probably say the instruction cache has more priority over prefetcher because the prefetcher is purely speculative and does not in any way actually prevent you from making progress, while your instruction and data cache can prevent you from making progress if they're starved. So one way to implement a prefetcher is you have a finite state machine where pretty much you'll say every time I get a miss, reset my my prefetch offset to 0, and then count up maybe like 3 or 4 cache lines, and then prefetch those ones. So that's what I would say. It sounds like a very like simple but also effective way to prefetch your cache. Again, there could be more complicated ones. For example, as you count up cache lines, you might decide I need to actually do a branch prediction because one of the instructions that I prefetched is a branch. And if I know that branch is going to be taken, or if I predict it's taken, then I should, instead of prefetching the next line, that's just PC plus 8, maybe I need to do whatever the branch target is and start prefetching from there. All right. Another thing you might also find useful when prefetching is for stores, right? Remember, stores cannot be committed until they are at the head of the ROB, but you often know the store's address well before it gets to the head of the ROB. So whenever store computes its address, you can have it prefetch that address into the cache so that it can more quickly commit by just writing into the cache. This would obviously be most effective if you have a write-back cache. So again, same thing. You can, with your MSHR, the MSHR algorithm is sort of good because, useful because you can sort of port all your prefetches, instruction requests, and your um, data cache requests into the same MSHR array. You can also have different arrays for those MSHRs. Again, it's up to you. But again, the idea is that every time you get a miss, you get a new MSHR entry, and then you look for entries wanting to send the request, and then you send that request once the response comes back as non-zero, and and then once the response tag matches that request, right, you'll kind of have you have like the memory is hooked up. The tag is like a broadcast wire, similar to the CDB, right, where every single MSHR is looking at all the tag at the same time, and only the ones that care about that tag are going to figure out, oh, I need that, right? That's my data. I'm gonna save that data and complete. Okay. And so this is just a summary of prefetching. So conservative prefetching ideas would be, right, get the next block, right? Usually, if I read one piece of data, probably going to get the one that's eight bytes away from it. And this one doesn't waste too much memory or too much bandwidth. The greedy strategy is says I'm going to march through memory. Now you can say how far to march, right? You can go one block, you can go 5 blocks. It's up to you. Um, and another, I guess, smart thing to do again for instructions. This is for your iCache. Is if you decide that the prefetch range you're trying to go across is a branch, then you will also find it's a good idea to try and say, oh, if this branch is taken, then I'm going to follow the prediction and not just go to PC plus 8, but go to the branch target. So that's the end of the slides. If you have any questions about the stuff, the staff will be available on Piazza. Thank you for watching.